Hi, in this video we are going to look at 3 examples of how to solve systems of linear equations using the substitution method. So diving straight in, the first thing says, step 1, look at our equations. Is there a variable that is isolated, which means all alone? So looking at both the top and the bottom equation, in the top I can see that y is isolated because it is completely all alone. So we are going to go down the yes path, that yes, we do in fact have a variable that is isolated. So now step 2 says substitute the expression for the isolated variable into the other equation. So starting off, let's get the expression for the isolated variable. So y equals 4x minus 9. So that's the expression for the isolated variable. And we are going to substitute that in place of y into the other equation. So that means anywhere we see a y in equation 2, we are going to substitute that expression from equation 1. So go ahead and rewrite that second equation. So 2x take away 4y equals negative 20. Right now we have 2 variables, but now we are going to substitute what we know y equals from this top equation in the box. So we have 2x take away 4, but instead of y, we are going to write 4x minus 9, since that is what y is equal to. All right, next step is step 3, which says solve that equation to find the value of our first variable. So go ahead and copy down what you had. So 2x minus 4 multiplied by 4x minus 9 equals negative 20. So we just copied down what we had from this last step. And now we're going to solve just like normal. So distribute, and then next step will be combining like terms. So 2x, this will be minus 16x plus 36 equals negative 20. And then combining like terms, we can combine the 2x and the negative 16x together. So this will give us a negative 14x plus 36 equals negative 20. And then show as much or as little work as you need to accomplish the rest of this. Check in with what your teacher's expectations are, of course. But our next step is to subtract 36 from both sides. And that will leave us with negative 14x equals negative 56. And then we will divide both sides by negative 14. And that'll end up giving us x equals positive 4. All right, so we have solved for one of our 2 variables at this point. Moving forward, we are going and following our arrow over to step 4 that says substitute the value of the variables found in step 3, so that is that x equals 4, into the equation with an isolated variable, and then simplify to find the value of that remaining variable. All right, well, we are supposed to go back and reuse this isolated expression equation. So y equals 4x minus 9. But thanks to the solving we just did in step 3, we now know that x is 4. So we will do some substituting there. So instead of x, we are substituting the value 4. And then if we do a little simplifying, 4 times 4 is 16. Take away 9 leaves us with 7. So now we have the value of our second variable. So at this point, I would believe that the answer is 4, 7, but we should always fact check and make sure that we didn't make any little baby mistakes as we went along the way. So our final step says check the solution by substituting the values for the variables we found back into both original equations. So our first original equation is y equals 4x minus 9. And then the second original equation is 2x take away 4y equals negative 20. So what we're going to do is everywhere it says y, we are going to write a 7. And then everywhere it says x, we are going to write a 4. And we're just going to make sure that the equations turn into true statements, since a solution is a value that makes your equation true. Or in this case, an ordered pair of values. So looking at our first one, we're going to check, does 7 really equal 4 times 4 minus 9? So you could either use order of operations, or if your teacher's okay with it, you could just type that into a calculator. But 4 times 4 is 16, take away 9 is 7. 7 does equal 7, so that checks out. So far, so good. But our values need to work in both equations. So going to the other one, we'll double check that 2 times 4 minus 4 times 7 actually equals negative 20. All right, so again, you could either do this all in your head, or you could just type it into a calculator if that's something your teacher's fine with. 2 times 4 is 8. 4 times 7 is 28. So this is really 8 take away 28, which is negative 20. So this checks out as well, which is perfect. Now just to format our answer, remember back from when you solved systems by graphing, that the solution to a systems of equations is where the two lines would intersect. So it really is a coordinate point location. And we always write our coordinates as x comma y, or if you have different letters, whatever that is in ABC alphabetical order. So for us, our final answer is going to be positive 4 comma positive 7. All right, so here was our first example. Moving on, here is example number 2. So starting at question number 1 again, it says, look at our equations. Is there a variable isolated completely all alone? This time there is not, because there is not an x equals or a y equals, which means we are going to be going down the no pathway. So now we have to do a little bit of extra work. So this pathway takes us down to isolate a variable. Choose the variable easiest to isolate in just one of the equations. Rewrite the equation to get either an x equals or a y equals. It does not matter, whichever is easiest. And as a tip, look for something that has a coefficient of 1 or negative 1. So something like an x or a negative x or a y or a negative y. Positive is easier than negative, but these are generally the least amount of effort to get something isolated. So looking at our two equations, I see two possible contenders. So in the top equation, I see an x, and then in the bottom equation, I see a minus y. It doesn't really matter which one we go for, but if something is already positive, that will save us some steps. So I am going to choose to target the x in equation 1 to get that isolated. So I am going to copy that top equation down, x plus 5y equals 2. And then I am intending to go for x. And again, you could have made a different choice. Really, you could have isolated any single one of these variables, but I'm just trying to go for the least amount of effort to get the job done, right? Maximum efficiency. So going to the equation that I have, if I want x isolated, I need to get rid of everything that is not that x. So I'm going to subtract 5y on both sides. And that'll give me x equals negative 5y, and then plus the 2 that was already there. So now I have rewritten this top equation so that x is isolated and I do have an isolated variable. So continuing on with our process, following the arrow this way, we are now on step 2, which says substitute the expression for the isolated variable into the other equation. So x was isolated and it equaled negative 5y plus 2. So I'm going to take that, and instead of using x in the second equation, I'm going to use the negative 5y plus 2. All right, so go ahead and rewrite that equation. But again, instead of x, we're going to use the isolated expression that we found by doing a little rearranging. So I'm going to substitute in negative 5y plus 2. All right, copying down our new equation that is in terms of y. Step 3 says solve that equation to find the value of our first variable. So we will do some distributing and combining like terms to get us started. And then just be very mindful of your sign. So a negative 4 times a negative 5y becomes a positive 20y. And then negative 4 times positive 2 becomes minus 8. And then take away y. Combining like terms, you can also think of this as a 1. We end up with 19y, take away 8 equals negative 27. And then keep solving to get your variable all alone. All right, so it looks like in the end, I am going to get that y equals negative 1. So now that we know that y equals negative 1, we are moving forward with our solving process. And step 4 says substitute the value that we just found, so that y equals negative 1, into the equation with an isolated variable, which is this x equals negative 5y plus 2. So go ahead and find your expression for the isolated variable and copy it back down. And then we will substitute y equals negative 1, and that will tell us what x is. So you can either use your calculator or multiply this in your head, but negative 5 times negative 1 would become positive 5 plus 2 more gives us x equals 7. So at this point, I feel pretty confident that 7 comma negative 1 is our final answer, but it's always best practice to check our work and make sure we didn't make any mistakes, because zooming out, you can see we did a lot of work to get here, and it's always possible that a small mistake was made along the way. Checking our work just allows us to find any mistakes and go back and fix it. So I am going to find both of these original two equations. So the first original equation is x plus 5y equals 2. And then the second original equation is negative 4x take away y equals negative 27. And everywhere we see an x, we are going to use 7. Everywhere we see y, we are going to use negative 1. And then we will just ensure that when we substitute this, we are left with a true statement, since we know solutions are values, or in this case, an ordered pair of values that makes the equation true. All right, so instead of x, we have 7 plus 5y becomes 5 times negative 1. We're just going to check that it equals 2. So this is 7 plus negative 5, also known as 2, which does in fact equal 2. So that checks out. Going to our second equation, negative 4 times 7 minus our y value of negative 1, we need to check is actually negative 27. So negative 4 times 7 gives us negative 28. And then right here, if you were really careful with showing your work, you would have found that this becomes a plus 1. So negative 28 plus 1 is negative 27. So this also checks out. One thing to be cautious of when we write our final answer is that you are not going to write negative 1 and then 7. While we did find negative 1 first, remember that we always write coordinate points as x, then followed by y. So your final answer will be 7, comma, negative 1. So this was our second example. Moving to our third and final example of solving systems equations using substitution, we have negative 5x plus y equals 7 and negative 3x take away y equals 17. And our first equation is still asking us if we have a variable that has been isolated. And while we have some that are close, no, we do not have any that are actually isolated. So we have to go down this no pathway again. And our reminder for this is to choose the variable that is easiest to isolate in either one of the equations. It could be an x equals or a y equals. A positive one is always going to be easier than a negative one, but anything with a 1 is easier than something like the negative 5x or the negative 3x, for example. No matter the variable, coefficients of 1s always take less solving effort. So looking at what we have, both of the y's look pretty enticing as options, but the top equation has a positive y, whereas the bottom equation has a negative y, and the positive will take less effort to isolate. So I'm going to start with copying down that top equation. And the variable easiest to isolate is going to be the y, which means we need to get rid of this negative 5x. So we will do that by doing its opposite or inverse operation. So add 5x to both sides. Oops, I over-erased on accident. Let's try that again. Here we go. So add 5x to both sides. This gives us y equals 5x plus the 7 that was there. And because I know what's coming, I'm already going to put a box around this because this is the expression for our isolated variable. So going and following our arrow to step number 2 says substitute the expression for the isolated variable into the other equation. We rewrote the top equation, so we are going to substitute it into the bottom equation. And everywhere we wrote a y, we are now going to replace it with what y is equal to, 5x plus 7. Now, one thing that you have to be really mindful of when you do this is we have 3x take away all of what y was. So make sure you put parentheses down. And then we are going to replace it with that 5x plus 7 from over here. All right. So that's it for step 2. Moving to step 3, copy that equation back down, and we are going to solve for x. So before I distribute, I just want to remind you that there really is an invisible negative 1 here that is going to get to distribute to everything in the parentheses. So this gives us negative 3x, take away 5x, also take away 7, equals 17. And then we can combine like terms. So this gives us negative 8x, take away 7, equals 17. And then from here, we'll keep solving like normal. We have a 2-step equation, so we will add 7 to both sides. So this gives us negative 8x equals 24, and then we will divide everything by negative 8, and being very, very careful with your signage here. We have a positive 24 divided by a negative 8, so this gives us x equals negative 3. Right? Odds are, if you were going to make a mistake at some point in this whole process, and then you get to the bottom and realize that your checks were not checking out, it's probably because you dropped a sign somewhere and maybe you got a positive answer where you should have gotten a negative answer or vice versa. So always just be really extra mindful of signs in this process. But we have an answer and we are ready to move forward. It says substitute the value of the variable found in step 3, so that's x equals negative 3, into the equation with an isolated variable, which is this guy. So y equals 5x plus 7, but we just figured out over here that x is negative 3. So we will substitute that. If your teacher's okay with it, you could just type this whole thing straight into a calculator, but we can do this in our head pretty easily. 5 times negative 3 is negative 15, and then negative 15 plus 7 gives us negative 8. All right, just to confirm our work, we will make sure we take the time to do our checks. So copy down the two original equations. The first one is negative 5x plus y equals 7. And the second equation is negative 3x take away y equals 17. So just like before, we will substitute what we think x and y equal. So everywhere there is an x, we will replace it with negative 3. Everywhere there is a y, we will replace it with negative 8. And we will make sure that after substituting this in, we are left with equations that make true statements. So negative 5 times negative 3 plus negative 8, we're going to check, is that really positive 7? So this would be 15 plus negative 8. Yep, that's 7, so that checks out. And then over here we have negative 3 times negative 3, which is positive 9. And then we're taking away negative 8. So one thing about that, taking away a negative becomes a plus. So this is really positive 9 plus 8, which is 17. So yay, that also checks out. So for our final answer, we just have to make sure it is in the correct order. So we will put x first, followed by y. So our final answer is the point negative 3 comma negative 8. And remember, if we were graphing these two equations that we have at the top, they would produce two lines that would intersect at the spot specifically on your graph at negative 3, negative 8. That's what our solution is telling us. So this was a quick look at solving systems of linear equations by substitution. Hope it helped. Bye.